Greetings, aspiring scientists. Welcome back. Welcome to my video today. We're going to start with chemical bonding, ionic bonding. Really the core of what chemistry is. It's taken many hours of video to get here. You know, you need an understanding of protons, electrons, neutrons, atoms, ions before we can really start talking about bonding. But we are here today with ionic bonding. Let's get started and go to my slides. So this is starting structure 2. So in some sense, we are 1/6 done the SL chemistry curriculum. We've done structure 1. So structure 2 is all about chemical bonding, as I said. And I think it does make sense to start with ionic bonding as the first type. So we'll start with 2.1, the ionic model. So first of all, ions. I've introduced what these are in previous videos. They are atoms which have lost or gained electrons relative to their starting natural state. So we have a guiding question in this section as well. It is, what determines the ionic nature and properties of a compound? So it's important to try to break down this question and see what it's really asking. What determines the ionic nature and properties of a compound? So it's not asking how are the bonds made, but rather what properties such as radius, charge, those kind of things determine what the properties of the compound will actually have. So before we get deep into ionic bonding, I just want to give you an overview of what type of bonding there really is out there. I think there's 4 main types. There is ionic in the top left here. You can see we've got alternating positive and negative ions. The example here I've given is NaCl. It's kind of the base ionic compound that's usually used for educational purposes. Underneath that, we've got metallic bonding. We've got some iron, and you can see we've got iron cations, Fe+, with some little blue dots floating around. Those things are electrons, and it's supposed to represent that they are free. They're not localized to any particular iron cation in that structure. They can move around as they please, but there will be some ratio of electrons to iron cations. Then on the right side, we've got covalent bonding molecular type. This is something like water, H2O, where we've got a pair of shared electrons in between hydrogen and oxygen on each side there. But the key thing that I want you to realize about covalent bonding molecular versus ionic, metallic, and covalent bonding network below it is that covalent bonding molecular behaves sort of like the ideal gases that we've studied in my recent videos, where the molecule, H2O for example, exists on its own, okay? There may be some interactions, intermolecular forces with other molecules of H2O or, solute particles around it. But compared to the other 3 types, the molecules exist on their own, okay? And then just underneath that, to go into a little more detail on covalent bonding network, this has essentially the same type of bonding as covalent bonding molecules, as in H2O, but each atom is bonded with various atoms around it in a repeating unit that forms a large crystal structure, trillions and trillions of atoms, wide or long or thick, however you want to think about it. So I just want to reinforce that covalent bonding molecular is quite a bit different than the other 3. Instead of each atom being surrounded by bonds all around it, it's very specifically bonded to some other atoms in the single molecular structure. That's going to explain why a lot of different properties happen, including strength and weakness and boiling point and melting point. Okay, so focusing on ionic. Well, first we can actually go into specifically how do we define several different types of bonding. So pretty much all bonding involves electrostatic forces. If you remember from my previous videos, electrostatics is the attraction between positive and negative, and the repulsion between negative negative and positive positive. So that force itself basically can explain all chemical bonding and most things that you see around you in the world. So Ionic, where will the electrostatic forces be, or where did they come from? It's between cations and anions. So cations being positively charged species which are lacking electrons, and anions being negatively charged species which have gained extra electrons from somewhere. When these things are nearby, positive attracts negative, we get some bonding forces that holds materials together. Covalent. What's the deal with this? Well, it's also electrostatic forces, but it's between atomic nuclei, the atomic nucleus, a positively charged region with protons and neutrons, and then shared electron pair or pairs in between several nuclei. Okay, that's what covalent will come to mean. Co means share, valent means valence, electrons, the outermost shell. And then metallic at the bottom here, we have electrostatic forces again holding it together, but this time it's cations like in Ionic, but instead of anions, we don't have anions in metallic bonding usually, but we have delocalized electrons, a lot of electrons that are freely roaming around. This gives it properties like good electrical conductivity, good heat conductivity, those kind of things. Okay, but we will be starting with Ionic. I think it's the simplest. So the standard ionic compound usually given is sodium chloride, NaCl. This is the table salt that you would put on your food to make it a little bit saltier. So it's fairly essential for living organisms. You don't want too much or too little, but if you can get a good balanced amount, it helps your body function. So you might not have thought about this before, but NaCl is a solid at standard temperature and pressure, and we can see kind of what the structure looks like by this picture here I made in ChatGPT. But we've got alternating spaces of sodium and chloride. The general idea is, what is next to a positive charge is a negative charge. Up, down, left, or right, whether you move forward, backward, side to side. What's surrounding positive charges is negative charges, and what's surrounding negative charges is positive charges. And I think if you get deeper into materials science and crystal structures, there's a million different ways that these can organize in like cubes or hexagons or diamond types of crystal structure. But we'll just assume that this NaCl is a cubic kind of type where you have these kind of like square shapes and cube shapes in the crystal structure. And we're just alternating positive and negative, cation and anion. Okay, so how is this going to form? Well, we need a sodium cation if we're going to make NaCl. So regular sodium has, on the left here, its elemental symbol Na for natorium, I think, from Latin or something. But it has 11 protons and 11 electrons in its standard normal atomic state, and it has 0 charge. So you can kind of see how those electrons are organized. There's some in the 1s region near the nucleus. There's some in the next level, in level 2, the 2s and 2p. And then it looks like there's one farther away, maybe the 3s1 electron, highlighted in orange there. So if this was going to lose one electron, which one is it likely going to lose? It's going to lose the farthest one away from the nucleus. That one feels the least effective nuclear charge. It's the farthest away. So if you're going to rip one off, it's very likely going to be that far away orange one. So we can imagine that happens, and then that outer energy level, level 3, becomes empty. So we'll represent that with a dotted line. We get our new sodium ion, cation Na+. It has only 10 electrons now, and it has a positive charge +1. But its nucleus is still the same as before. It's 11 protons, 12 neutrons for sodium 23, I guess that is. So in summary, what has happened here? One fewer electrons, different orbital configuration, different electron configuration. It's now isoelectronic with the most recent noble gas. It's got a different charge, +1, and it's got a smaller size. Basically, anytime you remove an electron, the resulting cation or oxidized species will have smaller radius because you have less repulsion within that atom now. Electrons usually repel each other, but if you remove one, things can get pulled tighter in towards the nucleus. Alright, how about chlorine? To make NaCl, chlorine will need to gain an electron. So we can start with chlorine here on the left, chlorine atom Cl. It's got 17 protons, 17 electrons, neutral, 0 charge. It's got these levels, level 1, 2, and 3. And it's got 7 electrons in that level 3 on the outer shell. So it's very close to having a full shell of 8 in level 3. Excluding the d electrons, we're not going to think about that for now. But if it could just get one more electron, it would have a stable noble gas configuration. So imagine an electron comes in from somewhere. We don't know exactly where in this case, but an extra electron comes in. Chlorine gains an electron, and we get chloride, Cl- on the right. We now have 18 electrons instead of 17. We've got a full shell of 8 in that level 3 in the orange ring outside. Nucleus hasn't changed at all. But in summary, what has happened here? It's gained more electrons, 1 specifically. It's got a different arrangement, different orbital configuration now. It's got a stable noble gas configuration, which is 1 electron above standard chlorine. It's got a different charge, it's -1, and it's got a larger size. Anytime that we add electrons into an atom, there's going to be more repulsion than there previously was. So those electrons are going to repel each other and expand a little bit and make the overall volume of that atom and the radius of that volume larger. Okay, so that's looking at sodium and chlorine in a vacuum and just adding or taking an electron away from them. So before we look at the full process, we kind of need to get into the naming system of these because we need to start referring to these things by their proper name. So there's a couple rules here. Anions, elements that become anions, usually change their suffix, the ending of the name, to IDE, pronounced Ide. Okay, cations usually do not change their name when joining a compound, although sometimes you'll see things like IUM appear, ium, like ammonia to ammonium. But if we're just talking about metals, alkali metals on the left side of the periodic table, they do not change their name. So I have a couple examples here. NaCl, that's what we're mostly looking at today. Sodium plus chlorine. So that INE, the Ne needs to change to DE. Ene to ide. This will generally be the case. So chlorine to chloride, that means we're going to name this sodium chloride. Next, iron, FeBr3, iron bromide. Bromine changes to bromide. We get iron bromide as the name of this FeBr3. But I have a little star here. Those of you who are a little bit farther ahead will know you can't really name something iron bromide because there's different types of iron, and it will confuse whoever is reading it. So in this case, this has to be an iron 3 type. It has a +3 charge, so you would normally write this like I wrote at the very bottom, iron bracket III, or 3 Roman numerals for 3, bromide. Okay, but that's getting a little bit ahead of ourselves today. There's another simple example underneath, ammonium plus oxygen. Oxygen needs to also change to ide. It's a bit tricky to know where to put the IDE in several of these, and it's just going to come from practice and reading and understanding where the suffix changes. Why is it not oxygide? Well, just isn't. There's no good reason for this other than someone decided it in the naming system. So oxide, and this will be named ammonium oxide. NH3, 2 groups of that attached to O. Okay. So if you want to go practice, I'm sure you can find some sources online or quizzes or whatever, or just try and name and create chemical formula yourself and try to name it, and you can check if you're right online. We also need to define oxidation and reduction. I think this might be the first time I've done this in my videos, but this is a hugely important concept that will appear again and again and again in organic mechanisms, organic chemistry, acids and bases, redox reactions. Pretty much everywhere you can think. Oxidation and reduction describes how electrons are gained or lost. So you can see here I've got species A and species B. If species A undergoes the process of oxidation, TiON, it will lose electrons and become oxidized. Notice how it's not necessarily positive or negative. It doesn't actually matter. It's just, did it lose electrons? If it did, it has undergone the process of oxidation. Now, if A undergoes the process of oxidation, B, as a part of this reaction, must undergo the process of reduction. B starts with some set of electrons, but it gains some through the process of this reaction, so it has undergone reduction. It sounds a bit weird to say that it gained something, but that's reduction, but it's because it gained electrons which are negatively charged, so its charge has reduced or become more negative. That's the way you have to think about it. It's going down on some kind of number scale, reducing to a more negative charge. Okay, so that's the base language you have to use, oxidation and reduction. But then there's the things on the left and right of this diagram. So if A underwent oxidation, in the end, it has been oxidized, ED. If B underwent reduction, it has undergone reduction, so it has been reduced with an ED. Bit of an English lesson here. And this is the part where a lot of people usually get confused, is on the left here. If A was oxidized, it began as a thing which can reduce something else, a reducing agent. Agent just means thing or thing capable of doing something. So a reducing agent can undergo oxidation and become oxidized. Similarly, something that has undergone reduction or can undergo reduction is an oxidizing agent. It will tend to take electrons from other things. This is also simply called oxidizers. This is how you'll see it labeled in like safety labeling and things like that. So reducing agents give electrons to something, they become oxidized. Oxidizing agents are hungry for electrons, if you want to think about it that way. They're much more stable if they could get electrons from somewhere. They undergo reduction and get reduced. Okay, hugely important. You can kind of think about this in terms of other English adjectives like, interested, interesting, bored, boring. If you are bored by things that are boring around you, right? But if you are boring, you bore things around you. This is how you have to think of reducing versus reduced, oxidizing versus oxidized. And you can't make a mistake in the way that you label these, otherwise you'll lose points on tests and reports and things. So try to get it right. Read a lot of descriptions of these things so you can see how they're used in different sentences. So clearly this applies to our discussion of ionic compounds, right? Because, as I just showed, sodium can be oxidized, lose an electron, and chlorine can be reduced to chloride by gaining electrons. And they can undergo a chemical reaction like this, shown on this slide. This one shows 2 electrons, but chlorine and sodium would only be exchanging 1 electron. Okay. So, oxidation states. We need to define this a little bit too. Oxidation states represent how many electrons an element has lost or gained. For now, you can think of this as the charge in the top right of the atomic notation. If, that should be of, sorry. So, you've probably seen element nuclear notation with possibly a number of protons or atomic weight or some charge in the top right as a superscript. These represent a type of oxidation state as well. And oxidation states extend beyond that a little bit, which we will learn in future lessons. But for now, that top right net charge of an element or ion represents its oxidation state. Okay, most elements gain stability when they reach a noble gas electron configuration of 8 electrons in their outer energy level. Okay, so things beyond helium and hydrogen just need to get their 2 electrons to be stable or lose all of the electrons. But things beyond that need to get 8. They need to fill their s and p orbitals to get a stable noble gas configuration. So this leads us to this idea of the octet rule. You'll hear this a lot. You'll be asked questions about this a lot. Which of these things fulfills the octet rule, which don't? Explain why. So the octet rule is 8 electrons in the outermost shell or outermost energy level. Does it have it or not? And you can predict that most atoms will attempt to get to this octet by losing or gaining electrons. So in our example today, sodium, for example, it's really close to obtaining a full octet. It just needs to lose 1 electron to go down to the previous level, which is filled with 8. Chlorine, on the other hand, just needs to gain 1. If it gains 1, it goes up to a stable octet of 8. Another example I have at the bottom there is O. O has 6 valence electrons in the outer energy level. If it could just gain 2, it would be very stable. So you can use this to predict how atoms will be expected to gain or lose electrons. So we can expect sodium loses 1, chlorine gains 1, oxygen gains 2. They'll most often go to their full octet and stable noble gas configuration. Okay. Next, so I've got here from Cloud AI the most common oxidation states for quite a few elements on the left and right side of the periodic table. Let's just not think about transition metals for a while in the D block in between, things like iron and copper. But if we just look at the far right and far left, this is what we've got. We've got metals and hydrogen on the left. So hydrogen and everything underneath it tend to go +1. They just need to lose 1 electron to get a stable octet. Right next to them is group 2. These need to lose 2 to get a stable octet, so that ends up being their most common oxidation state, +2. On the right, things can get a little bit more complicated. In group 13, starting with boron, things underneath that are basically all the same. They will tend to lose 3 electrons. That's still the fastest way that they can get an octet, or the easiest way. Go back down to the previous noble gas configuration, just like sodium, beryllium, magnesium, metals on the left. When we get to carbon, it says +4. That means it might tend to lose all of its 4 valence electrons in that sense. Silicon, germanium, and tin underneath it, similar idea. But I will say, if you're trying to get to 8, right, or 0 to go down to the previous level, 4 is kind of the place where it could go either way, right? You could either gain 4 and go up to 8, or you could lose 4 and go to 0, meaning you're at the previous noble gas configuration. So for this reason, I think these elements, especially carbon, are quite adaptive to their surroundings. They can either gain or lose. You might see carbon +3, +2, +1, +0, -1, -2, -3, -4. I think various combinations of these are possible, especially in organic molecules. Then we look at nitrogen, most commonly -3. It has 5 valence electrons, so it's commonly going to just gain an extra 3 to reach its octet. But underneath, in the nitrogen group, things get really kind of crazy. Phosphorus goes +5, loses all of them. That seems like a farther distance away than just gaining 3, but perhaps its nucleus just is too shielded and can't tend to attract electrons from other species. Arsenic and antimony underneath that, +3, so they don't go +5. Interesting. I can't really explain that why, but things sort of start to break down as you go down the periodic table, so different factors apply. We're not really going to go into that. But you can see The oxygen group follows what you would expect. It's 2 electrons away. It has 6 valence, so it needs 2 extra to get to the octet. Sulfur, selenium, and tellurium will basically behave the same. And then group 17, the fluorine halogen group, all of them just need to gain an extra. So they'll gain an extra electron to get their 8 electron octet. And then the noble gas, most common oxidation state is 0. They're already at an octet. They're already at a stable noble gas configuration, so they will not do much. They will not bond, except under extreme cases for the lower ones like krypton and xenon, it might be possible. But basically, we're looking at near the top of the periodic table, and we can see some of these trends follow what we would expect if these things are expected to try to reach an octet. I do want to make some notes about hydrogen as well. So hydrogen is a bit of an exception. It obviously will not form an octet, as it does not have any p orbitals. P orbitals are where those 6 electrons in a certain level would exist, but hydrogen doesn't have p orbitals. So hydrogen can lose an electron to become H+, which is just a single proton. However, it can sometimes gain an electron to make H-. You know, the stability of that is also fairly stable, the hydride anion, and that shares a noble gas configuration with helium. So you'll see both of these. I think H+ is quite a bit more common, but hydrides definitely also exist. They're useful reagents to do chemical transformations as well. And this is possible for some other elements, as I mentioned. For example, carbon. Carbon can go plus or minus, gain or lose electrons to reach its octet. So just be aware, the things I mentioned are guidelines. They're not strict rules. I would say that they get strict the closer you get to the sides of the periodic table, either the left side or the right side. Noble gases are 0. Chlorine and fluorine go -1, sodium goes +1, things in those groups. But when you get kind of in the middle, in the group 2, group 13, group 14 areas of the periodic table, things get more flexible for sure. Okay, ionic bonding. So, we've said sodium could lose an electron, chlorine could gain an electron. Well, what's going to happen if sodium loses its electron to chlorine? Maybe they collide, and a transfer of an electron happens. I have a little animation made by Claude AI here. Hope I can show. Go. Sodium. Electron goes to chlorine. It fills its shell to an octet. Both have an octet. One is minus, one is plus now, and they are attracted to each other. They form a bond. This is an electrostatic ionic bond between a positive cation and negative chlorine anion. So this looks fairly simple, but what I want you to get in your mind is that this happens again and again and again if you have, large samples of sodium and large samples of chlorine. And every time this happens, energy will be released, which will, I think, be released in the form of heat and kinetic energy, speeding up the other sodium and chlorine atoms around it. They'll collide, exchange their electrons, more heat's released in this kind of chain reaction, and these things pile up on top of each other, in front of each other, behind each other, to form that crystal structure that I showed near the beginning, where every chlorine is now a chloride and has positive cations around it, and every sodium is now a cation. It has negative chloride anions all around it. Alright, so ionic bonding. Typically, what we will have is a metal is oxidized by a non-metal. We'll talk about metals versus non-metals in the periodic table section of the curriculum later on, but you can kind of get the idea of what a metal is. They're the things near the left side of the periodic table that tend to go positive oxidation states. Sodium, beryllium, aluminum, those kind of things. Oxidized by a non-metal. These are things like oxygen, nitrogen, fluorine. Then both atoms have a stable noble gas configuration. The octet rule will be obeyed. Since a positive charge and negative charge are then in close proximity to each other, they attract each other, and they get stuck. Usually, many atoms undergo this reaction in quick succession to form a solid crystal structure. That's how we get our solid salt crystals. And that's basically all there is to it. So again, I'll show what this lattice might look like. Again, this is a solid crystal structure called a crystal lattice. You need to get used to this word, Lattice. Use it in all of your explanations for what structures look like. But it's basically a repeating, organized pattern of particles that have a set sort of repeating unit and spacing between the atoms. So it's important not to call this a molecule. You can call it a compound, but do not call it a molecule. Molecules are reserved for covalent molecular bonding. This is an ionic compound in a crystal lattice structure. All right, properties of this, what can we say? Ionic solids will form solid crystals. They will be hard and brittle, okay? Think about a big chunk of salt. Sometimes they form in whatever packages you buy, or if you've ever seen a salt mine, these big salt rocks. They are hard and brittle. They have high melting and boiling points. The crystal is an electrical and thermal insulator, so electricity will not flow through it well. Heat will not transfer through it well. They often dissolve well in polar solvents such as water. Okay, we'll get later into what polar means. But water is one of the best examples of a polar solvent. Salt, I'm sure you know, dissolves quite well in water. If you're ever cooking pasta, you put a bit of salt in, it's instantly dissolved in the water. Molten or aqueous salts conduct electricity well. This is an important point. So even though this salt as a solid is a good insulator, if you can manage to melt it by heating it up, hundreds or thousands of degrees to liquid state, you've probably never seen such a thing because it requires high temperatures, but that liquid state actually will conduct electricity very well. We'll talk about why in my next video. Also, if it's dissolved in water, similar idea. I'm sure you know salt water conducts electricity fairly well. Does not dissolve well in non-polar solvents. Okay, so you may not know what nonpolar solvents are, but these are things which are kind of opposite to water. They are things like oils, like gasoline or salad oil or vegetable oil, whatever. Oily things will not dissolve salt. And you can notice this if you go buy a bag of chips from the convenience store or whatever, and you see the little salt grains and crystals in little patches of oily liquid. Hopefully it's not that oily, but there's quite a lot of oil in quite a lot of junk food. Salt does not dissolve in it, and that gives you sort of the nice fatty and salty taste that you might crave. But these are properties of ionic materials. So it's best if you can start trying to remember these, and if you can, explain why. Again, we'll get into why in my next video. So, how do we explain that ionic compounds, the cations and anions, hold themselves together and form strong materials? Well, the best way that I would recommend to you is bring up Coulomb's law of electrostatics from physics. This is not necessarily something that you need to remember for the chemistry curriculum, I think, but you can and should use it, in my opinion. So there's an equation in physics, I think, discovered by the scientist Coulomb. The force of attraction, the electrostatic force, is proportional to the two charges, Q1 and Q2. So in our example, it could be the sodium cation and the chloride anion. So they have some number of charge in SI units of coulombs. So if you would increase the charge of either one of those, cations or anions, you would definitely increase the force between those cations and anions, the attraction. And because it's directly proportional, if you would double the amount of charge, you would also double the force. Double the amount of charge of one of those, okay? Double Q1, double F. Double Q2, you also double F. If you double both of them, you're going to times 4F. Okay, then this is all divided by R squared. R is the distance between those ions, okay? So as they get closer, this right side of the proportionality will become larger. The force will become larger very quickly. Okay, it's kind of like a inverse quadratic function. It's not linear. So as they get closer, the force gets much stronger. As they get farther away, R gets bigger, the right side gets smaller, force goes down very quickly. Okay, so if we have ionic compounds where the ions can get closer to each other, we're going to have much stronger forces, much stronger material. And then I have a note at the bottom here. Although force is not an energy, so you might not think it applies to, how much energy we put in to boil or melt the substance. Well, it actually does. Energy is very much related to the force, because if we want to break apart these ions from each other, we're going to need to remove the ions from the lattice. And that means applying our own force against the force of attraction. And as we do this over some distance, those of you in physics will know a force applied over a distance will require work, which is energy. So we'll need to apply energy to remove these ions from each other. However we do it, it's going to require energy. And vice versa, when this forms and these ions get close to each other, that releases energy, usually in the form of kinetic energy and heat. Okay, so I do want to talk a little bit about transition metals before I finish this video. So the transition metals are group 3 to 11 in the middle of the periodic table. So all transition metals can lose their s electrons. And also zinc is not included here. Zinc is group 12. It can also lose its s electrons to become cation and form ionic compounds. But here's the transition metals, scandium to copper, those groups. So you can see their electron configuration here. They've got S and then D. Remember that the exceptions of chromium and copper, instead of having 4s2, have a half-filled D for chromium and a full-filled D for copper. But when they go to ions, some of their most common ions will be just to lose the s electrons. So the s goes away. Chromium will also lose 1d to go to 3d4, and copper will also lose 1d to go to 3d9. These are all the +2 versions of cations, sorry. Most of these metals will have versions other than +2, but +2 is a fairly common one. So that's just what I'm showing on this slide. Now, what if we consider... Okay, some also lose further d electrons, that's true. What if we consider iron as an example, and we look at each ionization energy of iron for the first 12 electrons, it looks like here. So for the first 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, it's actually not that much of a slope. There's a big jump after that. That would be when iron were trying to go to the next energy level underneath. But for the first 8 electrons, we've got fairly lower slopes. So this graph can kind of be explained by looking at iron's electron configuration. 4s2, 3d6. You'll notice that is exactly 8 electrons as well. So if you remove those 8, you get to the stable octet noble gas configuration of argon. If you try to remove the next one, that's where this big jump is on the graph. So I also have this bit of a medium jump there. It's hard to see, but there is a bit of a difference in slope between 1, 2, and 3. This section here, maybe I can try a different color. This section here has that kind of slope. So it turns out the first 3 electrons of iron are very similarly easy to remove, okay? You'll see iron 2+ and iron 3+ all the time, all around. But the slope after electron 3 actually is significantly higher as you get into this kind of section. You might not notice that, but it's high enough that we actually don't see iron 4+ or beyond. Very often, anyway. I can't think of any examples of iron 4 or 5 or 6+ compounds. I think it just doesn't happen very often, and certainly not iron 8, 9, 10+. So you can try to explain common oxidation states by looking at a graph of ionization energy versus number of electrons removed, like I'm showing on this slide. And you'll fairly often be asked to explain changes in slope or big jumps in this way. Okay, so that's basically all I have to say about ions and ionic bonding as an introduction. In my next video, we will talk about what properties ionic compounds have, and specifically why they have those properties in relation to their ionic properties, such as radius and charge, and those type of things. Alright, so we'll stop there for today. Thank you for listening. See you in the next one.